Welcome everybody. This is the session on custom hardware for efficient computing. And in the program here, we're here, part 3, custom hardware for efficient computing. I'm going to begin with a little bit of overview of the state of the world. I'm going to begin with this presentation, with this slide, which actually shows the increases in the amount of computing that has been required over the last 10 years-ish for training deep neural networks. And the bottom line here is that rate has been increasing dramatically over the last 10 years. We're seeing an increase of 8 or 9 decimal orders of magnitude of increases in compute over that time interval. So what does that mean? What does that compute translate into? Well, at a very fundamental level, it means that we have to use compute elements at the silicon level. And so this is a rendition of the relative energy and area that's being used for, in the blue, is the compute elements for doing various sorts of computations, different sizes of addition, multiplication, and the relative energy of accessing data and moving data. That's shown in red, and showing where it is either comparable or much larger to move that data. So those large number of computes are going into this computation. Maybe a more intuitive way, or way to relate it more to what's going on in the environment, is to look at this chart, which is showing the carbon footprint for a variety of activities. What we see is, a round trip flight between New York and San Francisco is about 2,000 pounds of carbon dioxide equivalent. An average human life is 11,000. United States, that's 1 year, is 11,000 pounds. An American life is about 3 times that, just how much living for 1 year. An automobile over its lifetime is like 136,000 pounds of carbon dioxide. And those models that we were looking at before training are over 600,000 pound equivalents of carbon dioxide. So that compute we're talking about is using up a large amount of resources. So to address ways to improve on this situation, we have 2 very distinguished speakers. Our first speaker today is going to be Dr. Ahmad Bahai. Dr. Bahai received his master's degree from Imperial College, University of London in 1988. PhD degree from the University of California, Berkeley, 1993, both in electrical engineering. Upon graduation, he went to work for the wireless communications division of TCSI. Then he joined AT&T Bell Labs. He then was a co-founder of Algorix, which was acquired by National Semiconductor, which he worked for. He is now Senior Vice President and CTO of Texas Instruments, leading corporate research and the Kilby Labs. He's also an adjunct professor at Stanford. Over his career, he was involved in research and design of several widely used wireless standards, as well as ADSL and cable modems. He's one of the inventors of multi-carrier CDMA, known as OFDM, and is a fellow of the IEEE. I turn it over to you, Ahmad.
Thank you so much, Joel, and great to be here. It's an exciting topic, and I have 10 minutes and quite a few slides, so I'm going to jump into it. So as we all know, and as Joel mentioned, the energy management for data centers is becoming an important topic and challenging because of the demand for data. As we all know, we are living in a data economy, and it's going across the board. All segments of the market and technology has to do with the data. And in this chart, you can see this amazing exponential growth of data. And in many of these forecasts, we are underestimating what's happening. And what happened over the last 2 years because of the COVID, the data usage got accelerated to the point that people were dependent on data economy more than ever before for anything from entertainment to daily work to shopping and everything in between. So we see this trend is being accelerated. It's transforming all aspects of our life, and it ranges from the edge computing all the way to machine learning and cloud computing. And the size of the opportunity is growing, and all the estimates are, as I said, is kind of like understating what kind of change we are dealing with.
Ahmad,
Yes.
I'm really sorry to interrupt. This is Jeremy, but we don't see your slides advancing. So I think it's because of the way you must have shared them. We still just see the title slide.
Do you want me to go to this mode maybe?
Well, there it just did. Is that what, like it?
I'm back to kind of like out of the presentation mode. So maybe I keep it in that mode. It's easier.
I think so. I think so. It looks better that way. So,
okay.
Great. So now we see this data economy slide. Perfect. Thank you.
Okay. Yeah. So as I said, I mean, we see that this growth is exponential, and the exponent is growing because of what happened over the last 2 years. And obviously, power management and energy management is becoming more and more critical to enable this kind of like processing load. And it's not just the processing, but also the interface, the memory, and all aspects of it, which I'm going to talk about shortly. So what's the implication of the energy when we deal with this kind of growth? Of course, we have this exponent that is going up to about 9,000 terawatts hours of the energy over time by 2030. And that is the total energy estimate based on what's happening in the networks, wired and wireless, in the overall communication, production of the communication equipment and data centers and consumer devices, and of course the data center itself. And you can see all of them are growing exponentially, and the demand for more energy and power to feed this kind of processing capability is a big challenge for us in semiconductor, and I'll refer to that. Here we see that, you know, in terms of the compute, connect, and store, all of those are following pretty much the same exponents. And just the difference is that different applications have different levels of the intensity depending on the computing or connections or storing. For example, in the workload, we see that ERP, which is enterprise processing and other business applications, is taking a lot of workload, but search is dominant in a lot of other applications and loads. So it's kind of like it depends on how you look at it. But one of the most interesting parts that I wanted to highlight, which is kind of prelude to the rest of my discussion, is that PUE, which is really the power use effectiveness of data centers, have been making great progress over the last several years. Let me explain what PUE is. PUE is the amount of energy that is used in a data center over the amount of energy to run the processors. So it kind of like translates to the efficiency of the data center. So the closer to 1, it's the best scenario, because that means most of the energy is used really to drive the processing power that is the main purpose of the data center and not the overhead. And you can see that in hyperscale data centers over the last 8 years, we have made a great progress, bring it closer to 1. And that's thanks to many advances in power management, in architecture of the data centers, and many other factors. Of course, in this chart, I haven't included the blockchain and data mining, which is another interesting topic, that how it is pushing the data center power and energy management to the limit. Here is another example of how much progress we have made over the last several years in terms of the efficiency of these systems. On the top chart, you can see that if we had continued the same trend that we had with the same power management and same type of processors we used to have, we would have been at the point that the energy usage would have been much higher than what it is right now. But thanks to a lot of these innovations, we have saved about 620 billion kilowatt hours. Same thing on the communication side, the transition from 4G to 5G has been very efficient in terms of the overall energy consumption. But we see that this trend, in order to continue this trend, we are facing some real challenges on the device and circuits, and of course on the system side. So on the other hand, we see this massive growth of the semiconductor on all different markets, and semiconductor growth, of course, partly fueling this higher processing capabilities. You can see that memory for storage is a big chunk of that, and logic for processing, but also power management and everything else. And over the last 2 years, the demand for semiconductors is exceeding any expectations to the point that we have never seen anything like that before. But also the same semiconductor growth is now supporting more efficient power and energy management in these systems, which I'm going to talk about in a minute. Joel already mentioned that we have seen a massive amount of activities on AI and analytics, machine learning, accelerators, and of course the demand for higher power and higher energy is going up exponentially. And one of the big changes that's happening, which requires more innovation on all fronts, is that the Moore's law that we all have been expecting to help us on the overall performance as well as the energy and speed is slowing down, and we can no longer expect that the next generation of the lithography can solve the energy or speed problems. So that brings a multi-dimensional challenge, which is exciting for industry and for universities to explore many innovative ideas and not just depending on one vector that has been driving this innovation. So here is an interesting chart that was published about I don't know if you can see unfortunately I cannot put it in the full presentation mode because then my animation is not working for some reason. But here we can see that the expectation is if we had the Moore's law continued, we would have been like at the level of 219 terawatt hours by 2030. Whereas if Moore's law is not helping us, it would be about 491 terawatt hours, 70% increase almost in the energy usage of these data centers. And that means we have to get more innovative, and come up with other exponentials and other opportunities for us to really improve the energy efficiency. And of course, on the power efficiency and power management, the holy grail is that kilowatt per cubic inch that we are trying to get there. And that has some interesting device and circuit challenges that I'm going to talk about shortly. So what are the power management challenges of data centers? When you have these advanced processes or high-speed interfaces or advanced timings, then you need higher energy and power density, because with higher energy and power density, you can squeeze more power in a smaller form factor and not radiating as much heat and reducing the overhead of cooling. And also, the kind of voltage that you are providing to these processors needs to be much more accurate than before. So the point of load power management and power delivery is becoming much more challenging. The transients needs to be managed well. And a lot of these processors are switching between standby and full processing. And we need to learn how to do nothing better, I call it here. As you can see, how to wake up fast, but once we are in standby, you reduce the energy usage quite a bit. And that's what we can get inspired by our brain, how it works. When you are in shallow sleep, you're saving power significantly. I think our brain uses something about 10 to 20 watts, depending on what you're doing with your brain. But then when you are getting into shallow sleep, you get to 1 order of magnitude at least, or 2 lower power consumption, but at the same time, you have a very fast wake-up mechanism. You can wake up very quickly, not deep sleep, but in shallow sleep. And that's exactly the model that we need for some of these power management systems. How do we facilitate this massive amount of challenges that you're facing? Is that at device level, circuit level, packaging and thermal management, system architecture, we need to get a lot more disruptive as far as the opportunities for innovation. So one of these challenges is the emergence of 48 volt in rack power supplies. 48 volt is becoming a very interesting sweet spot for data centers and automotive. Now in automotives, a lot of advanced automotive power management is shifting from 12 volt to 48 volt. And same thing is happening in data center, but it's kind of like incremental way. So this is the past data center structure. In some cases, they're moving to a incremental 48 volts, but eventually we wanted to have fewer data conversion stages, because the fewer the data conversion stage you have, the more efficiency you get that translate to overall efficiency of the system. And adoption of that has been accelerated. We can see that in the past we had this 4 to 5 kilowatt power per rack, but now we have so many GPUs and so many advanced processes that's moving up to 10 to 15 kilowatt. And very soon, this is not a distant future, we're talking about a few years, we're talking about 20 to 40 kilowatt. And you can see that when we go to 48 volt versus 12 volt, which is today's most data centers are using 12 volt today, the efficiency goes up not only when you have full load, but in the light load also you have efficiency improvement. And any 0.1% of efficiency translates to massive amount of saving on cooling and overall efficiency of the system. So you can think of it as any 0.1% of efficiency increase is almost like 10% or 5 to 10% efficiency or reducing the loss. Today we have about 15% of data centers in this new architecture. Very soon we see it going up to 50% because of the demand for more advanced power delivery. Another angle which is kind of interesting, and I briefly talk about that before concluding my talk, is that it's not just how to distribute power within the rack, but also how to bring the power from high voltage all the way down to the rack and or point of load. And here's an interesting chart, a bit outdated, but very, very interesting in the sense that the penetration of the semiconductor in energy distribution in US in 2005 was only 30%. In other words, 30% of the energy in US goes through some kind of semiconductor conversion. And by 2030, the expectation is 80% is going to go through some kind of semiconductor. And that translates to at least a couple of billions of kilowatt hours energy saving. This red line is like the old way of doing the energy and power distribution, and semiconductor enabled version is the green line, which shows that huge energy efficiency, which translates to much smaller carbon footprint and so on. But that requires a lot of new devices, and one of the key innovations in that area is emergence of gallium nitride and silicon carbide as a commercial power management technology that can really reduce this for many reasons that we don't have time to talk about. Maybe later we can discuss it briefly. And here is how the future power transmission and distribution from well to wall, they call it, but from well to data centers, maybe we should say, is that this is how it works today. Many stages and many old transformers. In the future, maybe solid state transformers, in some cases DC line distributions and energy storage and renewables kind of tap into that and create an environment that we, rather than 12 volt, we are going to have 48 volts. So much more efficient all the way from high voltage down to the point of load. And I skip that and I conclude my talk with the fact that, you know, we have a tremendous opportunity here to make a change. Data centers and cloud services are going to go more complex and widely deployed. Data growth is up to 73 zettabyte by 2025. That's the expectation. Again, maybe higher than that based on the trend we saw in the last 2 years. And we see that the efficiency of these data centers requires fundamental advanced disruptive technologies on the processor design that I'm sure Bill is going to refer to that, power management, interface between processes, intra-rack and inter-rack interface, and high-speed communication, which is now going to 400 gigabit per second, and of course, timing and clocking of these data transfers and data processing. And that creates a very unique opportunity in semiconductor technology to play an important role in this transition. Thank you. And with that, I'll turn it over back to Joel.
Okay, thank you, Ahmad. That's really interesting. Now let me introduce our next speaker, Dr. Bill Daly. Bill received a master's degree in electrical engineering from Stanford and a PhD in computer science from Caltech. He has been a professor at both MIT and Stanford. He founded two companies, Valeo Communications and Stream Processors, and currently he is chief scientist and senior vice president of research at NVIDIA, where he leads work on everything, circuits, VLSI design, computer architecture, high performance computing, artificial intelligence, and networking. And I'm serious, he's involved personally in all of those things. Over his career, he has developed the system architecture, network architecture, signaling, routing, and synchronization technologies that are found in almost all large parallel computing systems today. He's a raft of honors. He's a member of the NIE, fellow of the AAAS, ACM, IEEE. He's won the Eckert-Mauchly Award, the Seymour Cray Award, Morris Wilks Award. And I want to finish by saying, some time ago, I learned that when two guys know each other for a long time, that what happens is that they actually know what kind of car the other one drives. And I know what car Bill drives, so I turn it over to my friend, Bill Dally.
Well, thank you, Joel. Let me present my slides. So in a slightly less elegant way, this is the same slide Ahmad showed that shows we have a problem. By many measures, data centers today consume, somewhere between 2 and 10% of the world's electricity, and they're on a growth path shown on this semi-log plot that will consume all the energy if we don't do something. The good news is there are big opportunities to do more computing with less energy. And to me, one of the most exciting opportunities is specialization. Building our computers so that they're specialized for a certain domain of applications. And this slide illustrates one project I did with a student at Stanford, who's actually now on the faculty at UCSD, where we built an accelerator for genomics calculations to assemble short reads of genomes into full sequences. And the core operation here is dynamic programming, where you take a query and a reference sequence and you apply the Smith-Waterman algorithm, the set of recurrence equations. And we compared even several generations of technology behind our accelerator to a state-of-the-art at the time Intel CPU. And what we found is that we are 26,000 times more efficient. And actually on the logic part of this, we're over 270,000 times more efficient than the Intel CPU. The bulk of the energy actually for this calculation goes into storing those red pointers, the backtracing pointers into memory, so you can find the optimal path later. How is this possible? Why is the specialized processing element, basically, 4.5 orders of magnitude more efficient than a CPU? And the reason is unfortunately that CPUs are horribly inefficient. If you look at doing a 16-bit integer add operation, and area here is proportional to energy, the energy taken for that 16-bit add, I don't know if I can show my mouse here, I guess I can, is this little red dot here. And the energy for all of the overhead, fetching the instruction, decoding the instruction, predicting the branch, managing the out-of-order execution, managing the speculation to roll back if you guessed the branch direction wrong, all of that is more than 10,000 times more expensive, 250 joules, picojoules versus 32 femtojoules, than doing the 32-bit add. So part of the reason why a specialized processing element is more efficient is that it gets rid of all that overhead, and then it gets a little bit of additional gain by collapsing several other operations down into one. Now, a lot of those watts that are getting consumed in the data centers these days are going to do training and inference of deep learning models. During the early days of AIs, it was mostly training, but now that we're deploying models and using them for a long time before retraining, it's actually now switching to be mostly inference, but training is still a big component. And what this chart does is it really sort of shows, how the role that overhead plays and the opportunities for efficiency here of 4.5 orders of magnitude between running your models on a conventional CPU. If you jump to a GPU, two things happen. The first is it uses what's called single instruction multiple thread control methodology. So we amortize that overhead cost over 32 threads. So we get a factor of 32 there. And then it's also a very simple control pipeline. We don't do speculation. We don't do branch prediction. So we get almost another order of magnitude from that. So you get close to 2 orders of magnitude going from a CPU to a GPU, just running on the basic instructions of the GPU. Starting with the Volta generation of our GPUs, we started introducing things we called tensor cores. And this is really a special purpose accelerator for matrix multiplication, and particularly for deep learning. So it's matrix multiplication using the data types that you want for deep learning. And that gets you another order of magnitude. So you're now about 3 orders of magnitude better than the CPU. And then Magnet here is an accelerator we built within NV Research that we'll be talking about at the VLSI Circuit Symposium this year. And it gives you about another order of magnitude and a half. And it's really sort of a prototype of what we expect to see in future GPU tensor cores. So let me talk about some of the ways in which we get this efficiency. A point that Joel made, showing the slide from Mark Horowitz, is that moving data is far more expensive than operating on it. If we take our 32-bit add, that little red dot on our energy illustration before, it's around 20 to 30 femtojoules of energy. Moving 64 bits, which is what you need to feed that 32-bit add, 2 32-bit input operands, is on the order of several picojoules. If you have to move it at 1 millimeter, that is. So I have to move it from one end of the chip to the other. I'm now running on the order of 100 picojoules, and going off chip is on the order of 300 picojoules. So it's really critical if you want to get efficiency that you keep things very local. And I'll come back and talk about this a little bit later. That's one of the ways that we, in our Magnet accelerator, achieve better efficiency than in the current tensor core in the Ampere GPUs, in that we very carefully optimize data movement using several levels of intermediate memories, these weight buffers, and also weight collectors and accumulation collectors, so that we can make this extremely efficient, move the data as little as possible. Here's an illustration of performance of our GPUs over the last 8 years. And it's also an illustration of efficiency, because all of these GPUs have about the same power consumption. It's illustrative to show where the gains come from. The early gains came from improving the data types. Originally, people were running on our Kepler GPUs, and it was basically all FP32. Google published a paper showing that their tensor cores on inference were way better than this. And actually, almost all of the gain was from running int8 instead of FP32. And we eventually got there in the Turing generation. But we quickly realized you can train most models with FP16, and you can amortize the overhead by doing dot product instructions. That was in our Pascal generation. We introduced tensor cores in Volta. So now we amortize that overhead of fetching an instruction over, depending on which instruction you use. For half precision, it's over 256 floating point operations. For the IMMA in Turing, it's over 1,000 integer operations. And that basically makes the overhead, that big blue area in that previous slide, essentially go away, because we're doing so much red for 1 unit of blue. Then in Ampere, we introduced structured sparsity. I'll talk a little bit about that later. And that accumulation has given us a 300-fold improvement in efficiency. So sparsity is one way of improving efficiency of neural networks, which is, one of my favorite sayings in life is never put off till tomorrow what you can put off forever. And it turns out for neural networks, you can put off doing a lot of those multiplies forever, because most neurons actually don't matter. Song Han at MIT and I wrote a paper in 2015 showing that you could prune the majority of connections out of neural networks and not lose any accuracy from them. It actually took a long period of time for us to figure out how to do that in a manner so that the irregularity of the resulting sparse computation didn't swamp the gain of reducing those operations. But in Ampere, we managed to finally crack the code. And the idea is structured sparsity, where we make only 2 out of every 4 weights non-zero. And then we can compress them with a little code which says which weights those are. That code is used to multiplex the input activations, and we wind up outputting just the dense output activations, and we uncompress them on the output. And that's a factor of 2 gain in efficiency. Number representation is also very critical. We published a paper at MLSys last year, basically trying to use those bits in the most information efficient way to encode the activations and weights. And it turns out this is a hard problem, because efficient isn't really getting the most information with the fewest bits. It's doing the most with the least energy. So, for example, using a code book is horribly inefficient, because that code book lookup and then resulting high precision math winds up swamping everything out. But what we found works very well is to do scale factors with small vectors. And this gives a huge improvement in efficiency, allowing us to basically do inference on a bunch of language models like BERT with half the number of bits previously required in the same accuracy. Now, in NVIDIA research, both on our own and in collaboration with Stanford and MIT, we've built a number of accelerators over the years to experiment with ideas to make deep learning more efficient. And I view these accelerators as basically prototypes of where we will eventually get with the tensor cores in our GPUs. So let me wrap up here. I think I've used my 10 minutes, and I don't want to let us slide any further behind schedule. A large and growing fraction of energy is being used by computing. So I think those of us in computing, have a duty to the planet to understand how to improve this. And the good news is that there's lots of room for improvement because the main engine we have for computing, our serial CPUs, are horribly inefficient. Their overhead is 10,000 times that of the typical payload operation. GPUs help. Just running normal instructions on GPUs is more than 2 orders of magnitude more efficient, both from the SIMT execution and by using a very simple pipeline rather than the very complex speculative out-of-order control of a modern CPU. But domain-specific accelerators can help even more. They have an opportunity to be anywhere between 10,000 and 1,000,000 times more efficient. We get that 10,000 right off the bat by just eliminating the overhead of a CPU. And then we can get another 1 to 100 times by specializing the operations. For example, doing those recurrence equations in the Smith-Waterman code, or specializing data types, particularly for deep learning or for some other computation. And so far, we've applied these to genomics, to deep learning, to a few other things. That GPU basically is a collection of domain-specific accelerators along with some very efficient general-purpose processors. But we've only begun scratching the surface. So a lot of other very demanding problems that I think we can be building accelerators for in physical simulation and optimization and so on. As we do this, though, we also have to realize that it's not just the operations, it's moving the data around. Communication dominates math, even moving a millimeter, and moving tens of millimeters or off chip, it completely swamps math by orders of magnitude. And so we really need to, as we move forward, develop our algorithms. I know there was a session earlier today called efficient algorithms. I'm hoping they're efficient in the right sense, in the sense that they optimize communication. One problem today is that we teach our undergraduates models of computation where reading a word from global memory is the same cost as doing that ad, when in fact they're about 5 orders of magnitude difference in cost. And these RAM and PRAM models I consider harmful because they lead to inefficient algorithms. They're algorithms that are efficient in the big O notation, but inefficient in the energy they use because they don't try to do more of the cheap operations to replace fewer of the others. So I actually have written a piece for CACM that should be appearing sometime in the not too distant future, where I argue for the need for a locality considering model of computation. So thank you very much. And I guess we'll move on to the debate.
Well, thank you very much, Bill. Both talks really enlightening and interesting. I don't know if there's really a debate so much as some questions. Ahmad, you gave some tantalizing tidbits about why that certain kinds of systems were showing improving efficiency. I'm curious why that was. So, for example, you noticed that when you compared traditional data centers to, in particular, hyperscale data centers, that there was actually a very significant difference there. Could you give us a little bit of insight into why that difference is there?
Yeah, that's a very interesting observation. I think the overall efficiency is going in many directions. Part of it is that if you save a single watt of the energy that is wasted, that translates to multi-dollars of the cooling and all that overhead that you have in these data centers. So one thing that data centers designers have managed very well over the last 8 years, in addition to what Bill mentioned in terms of improving the performance of the processor itself, improving the whole architecture. I mean, the power management now is a lot more efficient than what it used to be. They're reducing the number of stage of the conversion, which hugely benefits in terms of overall efficiency. The interface on chip between the chips and interface between the racks and between data centers, all of them have improved quite a bit. I mean, a very interesting trend in silicon photonics we see that is improving a lot of this communication structure. Also, we see that, the whole setup of these racks and how you position them in terms of the standby power versus full load power is becoming a lot more intelligent. In the past, a lot of power was wasted on standby mode. These servers have to be running almost full load because you don't know how much load you're going to show up, else who's going to wake up in the middle of the night and do searching or some processing on the cloud. So now we can wake them up much faster, so we don't need to keep them running at the full speed. So the beauty of that progress is that it's gone in many different disciplines and vectors coming together, but some of those are coming to the point of saturation. For example, this Moore's law type of thing, or using power management, a typical silicon. All of these are coming to the point that we have squeezed enough efficiency out of that and requires a next disruptive innovation. For example, going from silicon to gallium nitride can open up a very interesting opportunities for even more efficient power and energy management in the data centers. Is a DC bus the future for that? Some people believe in it, some people already are doing it, and some are evaluating. So that could be another step. So I would say at device level, at circuit level, and at system architecture level, we see a lot of interesting progress, and some of this progress are getting to the point that we need a step function in the disruptive ideas to get to the next level of efficiency.
So that's very interesting. You bring it up that way, because I was thinking along those lines when Bill started talking. Actually, although this is not a debate, it's not only supposed to be between me and each of you. That you
let me comment a little bit on Ahmad's comment in two ways. So first of all, let me make a comment about PUE, because I think PUE is an extremely bad measure of efficiency, and the reason is the easiest way to get better PUE is to run your servers at a higher temperature, right? Because then you wind up using less energy in the air conditioning, which counts in the bad side of the ratio, and more energy in the compute, because all the extra leakage that gets caused by running your servers hotter gets counted as compute energy because it's being dissipated by your CPUs and GPUs. But in fact, if you look at the real measure you care about, which is ops per watt, reducing PUE by turning down your air conditioners makes your ops per watt worse. You get fewer ops per watt because you get more leakage energy out of the CPUs and GPUs. I think it's really critical that we use the right metrics in measuring efficiency. There's a great NCAR paper where they optimized a data center in Colorado and showed even though it didn't have state-of-the-art PUE, it was actually more efficient than some data centers, for example, that Facebook built up in Oregon that have very good PUE, because they found that running the CPUs cool was actually a better way of getting PUE. But I think the other point I'll make is that I think we've made huge strides in making our power management, power delivery more efficient. But once you get to the 96, 97%, you've only got 3% left. I think we're only beginning to scratch the surface on making the compute more efficient. I think that there's, on the order of 4 or 5 orders of magnitude to be had in the movement from very inefficient CPUs to extremely efficient domain-specific accelerators. And so, we can decide where to apply our energy to try to crank that last 3% out of where we're already doing a great job, or to try to apply some energy to get a few orders of magnitude of where we're doing a really cruddy job by some measures.
Yeah, I agree. I mean, Bill, that's definitely a big, opportunity for innovation. But also, I mean, in power management, that 3% sometimes is misleading, because 0.1% means that 0.1% of 3% loss, which is all the cooling infrastructure is built for. So it means that could be 10%, 20%. So literally, if I can take it from 96%, and I have some numbers in my notes, I don't have it right off the bat, every watt is going to be about $2 saving. Mm-hmm. So we can imagine that 1% could translate to, the terawatt kind of a situation. You're talking about 1% of terawatt. That means like a huge saving if I can shave off that 0.5%. And it's a very tough problem, but it's doable with these new devices. So that's exactly the way I look at it. Sometimes talk to these data centers guys. Do you really care about 97.1 to 97.3? They said, yeah, it's 0.2% of the 3% that is left for us to save all these overhead, and that is huge number for them. So it's really kind of like all have all of them have to go hand in hand. And plus the fact that transient performance of these power managements for new processors are a lot more strict. And that's why it's putting a standby power challenge on some of these power management systems. Because if you want the perfect transient, you cannot shut off the power management completely and wake them up cleanly. So a lot of interesting high performance power management and energy management issues are coming up, which really makes a big difference on some of these carbon footprint issues.
Okay, very good. So I was starting to say, Ahmad had talked about the need for innovation, and certainly when you were starting to talk, Bill, about the slope here of the amount of compute we need and the amount of energy that can be produced, it reminds me of I think it was turn of 2 centuries ago problem that was posed, where they were looking at the growth in the number of telephone operators they needed with the growth of the telephone network, and concluded that they needed more operators than the population of the world. And the way that was addressed was with big innovation, right, where you eliminated the need. So I'll first turn it to Bill. Do you see a potential for that big an innovation?
Yeah, I do. I don't know that it's quite the same as replacing operators with electronic switching systems, but I think that we still largely do most of our computing on these horribly inefficient CPUs. And as we move to a world where it's mostly done on domain-specific accelerators, there's huge amounts of room for innovation. In fact, it's mostly a programming problem. Building an accelerator is 90% casting the problem as a sort of locality-efficient algorithm, and 10% then lowering that into hardware. And so I think that the innovation is in that efficient programming. And if we can do that, we're not going to shave a few percent off these terawatts. We're going to shave 90%, 95% off those terawatts, and that's even more terawatts. So there's huge opportunities for innovation.
Ahmad, did you have any other comments on that?
Yeah, I mean, I feel what's exciting is that innovation is across the board. Like Bill said, I mean, there's a lot of innovations on CPUs and special accelerators. I mean, replacing CPUs with specific application domain kind of accelerators, but also on interfaces, on the timing and clock references, and on the whole power management delivery. All of them are getting to a point that, let's say 1% shaving the loss means 30% reduction of these cooling and heating cooling systems overall. And I think the innovation on that front is not just the topology, it needs the new devices. And that's why we're excited about things like gallium nitride that really can increase the switching frequency of some of these power management systems, orders of magnitude, and then translates to so much power density improvement that we can get. And all of these are bringing a new way of thinking. I mean, the silicon photonics for interfaces opened up a new door for innovation. So device innovation is becoming very critical for a lot of these applications. And as you said, the device innovation is not happening overnight. There is a lot of research and deep collaboration between industry and university tends to bring something like a gallium nitride from a concept to a commercial product. I mean, I don't think any single industry, no matter how big they are, can afford to do that, because what happened in CMOS, it was a collective effort across the entire industry. Almost the entire industry collaborated, and universities, to get to where we are after 30 years of making it almost a flawless technology. We don't have that luxury for these new materials because we don't have the entire workforce and critical mass behind that. So I think innovation on device level is going to be the one that really requires more patience and more critical mass. But that ripples through the entire value chain of innovation on circuits, on architecture, on system design, and so on.
So you bring up a very interesting point. So, what we've heard here is that there's actually many points in the stack for which, innovation can contribute, and that probably the solution is, potentially a more holistic view of all these pieces. So what do you see as the critical partnerships or mechanisms or collaborations that are going to be necessary to make this happen between industries, between industry and university, and how might that best be structured or focused?
Bill, you want to go first? You're involved in many of these.
I think, if I look at where I see the big gains coming from, sort of extending domain-specific accelerators to more domains, it's really a partnership between fields. So what I've found is that it's impossible for a computer scientist to just go and do a good domain-specific accelerator for new domains, say climate simulation or convex optimization, because taking the existing algorithm, which has been highly optimized for serial CPUs, is usually almost always completely memory limited. And if you try to take that and just accelerate it, you get a factor of 4 or 5, maybe 10 on a good day. But if you understand the problem well enough that you can refactor the algorithm and say, okay, here are all the things that are using lots of communication. Let's do fewer of them and more of the things that are cheap. All of a sudden, you get factors of 10,000. And a great example here is when we did our genomics accelerator, I talked about the Smith-Waterman part of the problem. The other part of the problem is the filtering part, finding the candidates to feed into the actual alignment. And the traditional codes that we were looking at, Minimap and the like, basically spent all of their time on that filtering because on a conventional CPU, the dynamic programming is very expensive. But that filtering is completely memory limited. So we had to refactor the algorithm to do less but more efficient filtering and then make up for that by using more alignment. But it's the exact same thing you need to do in any case, is do less of the expensive thing, more of the inexpensive thing. But it requires somebody who's an expert in the field to do that. So I think we're going to have to build lots of partnerships between computer scientists on one side and domain experts on the other side, be they climate experts or optimization experts, whatever problem you're solving, to come up with really efficient engines for those problems.
Ahmad, did you have any comments on?
Yeah, I agree. I mean, collaboration has different elements to it. Like Bill said, across disciplines. I mean, people from different disciplines need to converge on some of these opportunities because most disruptive innovations are at the edge of multiple disciplines. But also on some of this foundational stuff, like new materials, collaboration between industry and university is very important in a sustainable way because it takes time and takes a lot of effort and money and critical mass of brain and funding and resources. So there are different directions across disciplines and across different organizations to make that happen. And again, when it comes to a manufacturable, reliable new material, it takes a lot of patience and money.
I think we need partnerships with universities to educate a crop of computer scientists who are locality aware. We need to stop teaching them the big O model of computing with RAM and PRAM and start teaching a way of thinking about algorithms that are energy efficient.
That's a very good point. I'm asking one more sort of related question, which is, what do you see as the sort of the barriers to making these things happen? You talked about education. You talked about importance of fostering collaboration. Ahmad talked about the different levels of the stack that the innovation needs to happen at. What would you say are some of the barriers?
Well, there are huge barriers having to do with sort of inertia and especially software inertia. There's enormous numbers of lines of code out there that run on inefficient CPUs, and those lines are solving people's problems today. You're not going to change that overnight. And so
they don't want to stop using that big Fortran deck.
Well, it's worse than big Fortran decks in a lot of ways. But I think that is inertia is the big obstacle. I think one advantage that Ahmad has with power delivery is, if I have a power converter and it takes 48 volts in and it puts out 0.7 volts for the GPU, I have a more efficient one. I just plug it in, align it. Actually, a few lines of code in power management probably do have to change, but very few lines of code have to change. Whereas if I decide I'm going to take some 100 million line, code that is doing some, transportation optimization problem and say, okay, guys, use this really cool accelerator thing here. I mean, I have a huge compatibility and installed base problem.
That's true. But Ahmad, do you want to talk about how easy it is to convert from 12-volt racks to 48-volt?
Yeah, it took us 10 years to convince some of those to change from 12 to 48 because they, like Bill said, I mean, changing the whole software stack is kind of an enormous task. There's a lot of resistance to do that. But on the hardware side, once people feel something is working, I mean, they have to see a big problem with that to replace it with something better. So the question is must have versus nice to have type of thing. And that takes a kind of like a transition of a few years. But you're right that we don't have the kind of inertia of the software. But the other angle is, I think, the competitiveness of the market, especially in semiconductor, is so fierce that, it leaves very little room for even big companies the size of TI to spend a lot of bandwidth in terms of people and money on disruptive technologies, because you have to keep running. And that's where it makes it more efficient to get hopefully government and universities involved to support some of these things, because competition is a matter of, shaving a tiny 1% from either cost or improving performance. And that makes a huge difference. And that is an endless race that we are all in. So I think that's another challenge that we all are facing. But at the same time, without those innovative, disruptive ideas, we are not going to get the next big step function that we all expect. I mean, look at what happened after Bell Labs demise. I mean, how many new transistors kind of ideas have popped up, I mean, because we need that kind of critical mass and continuity of research to drive the next big thing.
So I want to make sure that the audience knows that we're open to questions from the audience, and please put them in the chat, and I will convey them to the panelists here. We do have one for Bill, and the question is: do you have any measurements of the energy efficiency gained from the compression of large neural networks that you talked about?
Yeah, so I can answer that in a couple ways. So there are a couple different levels of compression, and from some of our early work compressing, multi-layer perceptrons, where we get compression rates, on the order of 10 to 1 or so, we were able to basically make them 10% dense. The energy efficiency is comparable because a lot of the energy consumed is actually reading the weights from memory, and we just don't read the zero weights. And then on Ampere, where we do the 2 to 1 structured sparsity, the energy efficiency gain there is actually almost exactly 2 to 1. We're basically doing twice the work in the same amount of energy as if we did it without turning that feature on.
There's another question, which is, what are the industries that are not experimenting with more efficient computing that should be? I'll turn that to Ahmad first.
It's interesting. I mean, computing is becoming so common and so critical for every industry that now a lot of companies are outsourcing their cloud computing to major service providers. So I think a lot of industries are moving away from having their own server room and go to the cloud, as far as a lot of analytics and a lot of ERPs that they are doing. So we see that is helping the trend across the board and permeating every aspect of industry. Still, there are a lot of edge computings that I wouldn't consider it as in this data center concept, but how to do things, analytics at the sensing point, or where the industry needs to measure something and remove the noise at the sensing node before transferring it to the cloud. So I don't think there is much resistance against using the efficient computing, because computing is getting outsourced to major cloud service providers. That's a good thing because that's more efficient. And in addition to that, with encryption techniques improving quite a bit, people are more comfortable even for data, for sensitive confidential information, still pass it to the cloud. So I cannot pinpoint a single industry that is resistant against that, but I'm sure it has very variable degrees across industries. So,
well, there's certainly a lot of worry now about, even if the data is encrypted, that there are vulnerabilities both in the software and in the hardware for leaking that information.
Correct. Correct.
Yeah.
And that's why homomorphic encryption is becoming very hot. And variations of homomorphic, and there are quite a few.
How do we use more computes to do the same thing?
Yeah. Now, what I've observed, especially back when I spent more of my time visiting NVIDIA customers, is that almost every industry is experimenting with more efficient computing. So, I would spend time talking to people in the financial industry, in the energy industry, simulating oil reservoirs and the like. But I think the gap was in moving from experimenting to deploying. And I think for all of these industries, it was a calculation of, I've got some big code deck that runs on some inefficient CPUs today, and it would take a lot of programming effort to move it to be 100 times more efficient running on GPUs, and even more effort to build an accelerator for it. And most of them have done some cost return calculation and decided, it's not worth the cost today to invest in actually deploying the more efficient solution, even though they've experimented with it.
So that sort of touches on a very interesting point, which is often, sort of local optimum for a company on making these decisions are not necessarily global optimum. And so especially in this, global domain of saying, well, we want to reduce CO2 emissions, make more efficient computing global.
Well, a carbon tax would go a long way to making those two align, right? You have to make people,
right. So that was my question. So do you see, basically government policy having a role to play here in nudging the world?
Yeah, I think so. I think trying, and I think the government policy has to do the right thing, which is to create the right incentives for people to operate in a sustainable manner. And so, there's very few penalties today to put a lot of CO2 in the atmosphere. You don't have to pay for it, but you cause huge externalities, and you need to internalize those. And I think the most efficient way to do it is simply to have some fee for putting carbon in the atmosphere. And then don't tell people how to do it, right? The market and a lot of really clever entrepreneurs will come up with clever ways of reducing carbon emissions if there's an economic incentive to do so. But if you don't have that economic incentive, it may wind up saying, okay, I could spend a lot of energy, running my old codes on inefficient computers, or I could pay a lot of programmers to recode them and run it more efficiently. You may choose to do it inefficiently because there isn't any penalty for the carbon.
Right. The slightly higher electrical cost doesn't outweigh the externality of the carbon costs. Okay. So we're actually nearing the end. So I'll let each of you, Ahmad, if you want to give some closing thoughts.
I think.
Sorry, I was going to turn it over to you to talk about policy as well. So you can combine that.
Actually, Bill pointed out the key issues, but a lot of people think that since computing and data center is only 1 to 3%, the aluminum sintering is using a lot more power. So why should you worry about data centers? But the fact is that it's growing so fast, and it's kind of getting to a point that everything in our life is somehow depends on those things. So it's becoming a big challenge for us, but at the same time, it's an exciting opportunities for more innovative ideas across the board. And that makes it fascinating and a field which has impact on our efficiency, but also on the quality of life down the road. So I'm looking forward to a lot more collaboration across the board to solve some of those problems.
That would be great. Bill, do you want?
Yes, let me just second what
I wanted to talk to you about I wanted to ask you about the contrast between flexibility and domain specific, but
it's time for closing. I have like 1 minute for closing arguments. So let me close. We can do that conversation offline. I want to second everything Ahmad said. I think that data centers are already significant. It's many percent fraction of electricity consumption, and growing so rapidly that I think it's incumbent on us to make them more efficient. And the very high overhead of the way we do things today, it's kind of like the obesity crisis in the US. We need to slim down the way we do computing. And there's some huge financial obstacles to doing that. It requires recoding things to run on GPUs, which is expensive. It requires developing domain-specific accelerators, which is even more expensive. But to create the economic incentives to do that, we need to create the right, financial incentives to make it worth people's while to invest in being more efficient. I think we know how to do it. There could be innovation is required, but we know where to sort of focus the really smart people if the economic incentives are there.
Okay, well, thank you very much for a very enlightening panel. I really appreciated your presentations and comments and conversation. So thank you very much.
Thank you.
I'm going to close. It was nice meeting you, Ahmad.
Thank you, guys. Thanks,
Nice
Ahmad.
meeting you too.